Good morning everyone. Today I'll be presenting a survey of the paper World Models by David He from Google Brain and Jürgen Schmidhuber from NNAI Sense and Swiss AI Lab ITSIA. This paper was published in 2018 and asks a deceptively simple question. Can we train an agent to learn entirely inside its own imagination? Let us find out. Here is the roadmap for today's talk. We'll start with the motivation behind world models, drawing parallels to human cognition. Then we will walk through the three-component agent architecture. After that, we will look at two concrete experiments, a car racing task and VizDoom task, where the agent trains entirely inside a dream. We will close with a discussion of iterative training and the limitation of this approach. The starting point of this paper is the observation that humans do not interact with the real world directly. Instead, we carry a compressed mental model of the world inside our heads. J. Wright Foster, the father of system dynamics, described this beautifully. The image of the world we carry in our head is just a model, a selective set of concepts and relationships that we use to represent a much larger real system. The brain learns abstract representations of both space and time, and crucially, what we perceive at any given moment is actually governed by our brain's predictions about the future, not just what our senses are currently reporting. This predictive nature of perception is illustrated by optical illusion, like the one shown here from researcher Kidalga. Our visual system fills in motion and structure based on learned predictions, not just raw pixel data. A striking real-world example is baseball. A batter has only milliseconds to decide how to swim, far less time than it takes for a visual signal to travel from the eyes to the brain. The reason professional players can hit a 100-mile-per-hour fastball is because their muscles act as a subconscious internal prediction. There is no time to plan. The model just fires. This is exactly the kind of fast, reflexive model-driven behavior the authors want to replicate in an artificial agent. Now, in reinforcement learning, most model-free methods use surprisingly small neural networks. The reason is that credit assignment problem. It is very hard for our algorithms to train millions of parameters reliably. So in practice, researchers keep the policy network small, but this sacrifices capacity. The key insight of this paper is to separate the agent into two parts: a large world model that absorbs most of the complexity, and a tiny controller that just maps representations to actions. The world model is trained with supervised or unsupervised learning, which scales well. The controller is kept so small that even simple black box optimizers like evolution strategies can handle it. The agent has three components. First, the vision model, or V, which takes a raw image frame and compresses it into a compact latent vector Z. Second, the memory model, or M, which takes the history of Z vectors and actions and predicts what Z is likely to look like next. It maintains a hidden state edge that summarizes everything the agent has experienced so far. Third, the controller, or C, which takes Z and H as input and output and action. The key design principle is that almost all of the parameter and complexity live in V and M. C is intentionally minimal. The V model is a convolutional variational autoencoder. It resizes every frame to 64 by 64 pixels and passes it through 4 convolutional layers to produce 2 vectors mu and sigma, each of size nz. The latent vector z is then sampled from the Gaussian distribution, defined by 3 parameters. A decoder with 4 deconvolution layers reconstructs the original image from Z. The model is trained by minimizing a combination of reconstruction loss and KL divergence. The Gaussian prior on Z is important. It constrains the latent space and makes it more robust when the M model later generates Z vector during hallucination. For the car racing task, Z has 32 dimensions. For the Doom task, it has 64. The M model is a mixture density network combined with a recurrent neural network, specifically an LSTM. Its job is to model the probability distribution of the next latent vector Z given the current action, the current Z, and the RNN's hidden state edge. Rather than predicting a single deterministic next frame, it outputs the parameters of a mixture of Gaussians. This is crucial because many environments are stochastic, and a deterministic prediction would be overconfident and easily exploitable. The temperature parameter tau can be adjusted to control how spread out or uncertain the model's predictions are. We will see why this matters when we get to the Doom experiment. The MDN-RNN architecture was previously used in Sketch-RNN, a model that generates human-like sketch drawings by predicting the next pen stroke as a mixture of Gaussians. The authors adopt the same architecture here, but instead of predicting pen strokes, they predict the next latent frame Z. The mixture of Gaussian output is particularly well suited for environment with discrete random event. For example, whether a monster decides to fire a projectile or stand still, a single Gaussian would struggle to represent these sharp multimodal distribution, but a mixture can naturally capture them. The controller is deliberately as simple as possible. It is a single linear layer that takes the concatenated vector of zt and ht and maps it directly to an action at. For the car racing task, this means only 867 trainable parameters in total. Because C is so small, the authors use CMA-ES, covariance matrix adaptation evolution strategy, to optimize it. CMA-ES is a black box evolutionary optimizer that works well for up to a few thousand parameters. It is embarrassingly parallelizable. You just bomb many workers, each running a rollout with a different candidate solution, and collect the cumulative reward. No gradients needed. The design means the credit assignment problem only needs to be solved over a tiny parameter space. Here is the complete loop in pseudocode. At each time step, the current observation is encoded by V into Z. The controller takes Z concatenated with the RNN's hidden state edge and outputs an action. The environment steps forward, returning the next observation and reward. The RNN then updates its hidden state using the action and the Z just taken. This continues until the episode ends. Notice that the reward signal is only ever used by CMA-ES to evaluate the controller. The road model V and M are trained entirely without reward, purely from observations. The first experiment is car racing-V0 from OpenAI Gym. This is a top-down car racing environment where a new random track is generated for each episode. The agent controls 3 continuous actions: steering, acceleration, and braking. The task is officially considered solved when the agent achieves an average reward of 900 or more over 100 consecutive trials, which means it can afford very few mistakes. The training procedure is: first, collect 10,000 random rollouts to train V and M, then use CMA-ES to find the 867 controller parameters that maximize cumulative reward. Critically, the road model never sees any reward signal. It only learns to compress and predict observations. This figure shows the VAE's reconstruction quality. The top row shows original frames. The bottom row shows frames reconstructed from the 32-dimensional latent vector Z. The reconstruction is lossy. Some fine details are missing, but the essential structure of the road, the car position, and the upcoming track geometry are preserved. This is enough information for a controller to learn to drive. The V model is essentially performing a kind of learned JPEG compression, but one that preserves task-relevant structure. This is one of the most important results in this paper. On the left, we see an agent that only has access to ZT from the VAE. It cannot see the RNN's hidden state HT. This agent wobbles, missing sharp corners, and scores only 632 on average. On the right, the full world model agent has access to both ZT and HT. The driving is dramatically more stable, and the agent attacks corners confidently. The reason is that HT encodes the RNN's belief about the probability distribution of the near future. The agent does not need to plan ahead explicitly. It can just query this compressed future belief instinctively, much like the baseball batter we discussed earlier. Here are the quantitative results. Deep RL baselines like DQN and A3C score in the 343 to 652 range. The best reported result on the OpenAI Gym leaderboard before this paper was 838. The full world model agent achieves 906 plus or minus 21, officially solving the task. This is also the first reported solution to car racing V0. Notably, the agent works directly from raw RGB pixels with no hand-engineered features, no edge detection, and no frame stacking. All the prior methods that worked well require these tricks. Because the M model can predict ZT plus 1 from the current state, we can use it to hallucinate an entire environment. Instead of stepping the real GAN engine, we sample ZT plus 1 from M's predicted distribution and render it through the VAE decoder. The controller trained on real environment can then be deployed inside this hallucination or dream, and it mostly works. This figure shows the agent driving inside its own imagined world. The user can also adjust the temperature tau interactively on the paper's website to see how uncertainty changes the visual quality and difficulty of the dream. The second and more ambitious experiment is the VizDoom Take cover. The agent is placed in a room and must dodge fireballs shot by monsters. There is no explicit reward. Survival time is the reward. The episode runs for up to 200 and 100 steps, and the task is solved at an average of 750 steps over 100 trials. The key difference from the car racing experiment is that here, N is also trained to predict a binary DOM signal, whether the agent dies in the next frame. This gives the world model everything it needs to serve as a complete standalone RL environment. The agent will train entirely inside M without ever touching the real GAN engine during training. So this figure shows the agent navigating inside the hallucinated Doom environment. The M model has learned purely from random rollout data to simulate the essential aspect of the GAN, the 3D graphics rendering, the movement physics, the enemy behavior, and the fireball trajectories. It even learns boundary conditions. If the agent tries to move past a wall, the model learns to stop it. The latent space training has a major practical benefit. No engine needs to run during training. The drain is purely a sequence of latent vector predictions, which is computationally cheap and can run on CPU alone. This figure shows the agent. This is already done. Okay. Here we encounter a fundamental problem with training inside a learned model. Because the raw model is only an approximation, it contains imperfections and blind spots. A controller optimized by CMA-ES discovers three imperfections and exploits them. In some rollouts, the agent found a policy where the monster simply never shoot fireballs, not because the agent is good at dodging, but because it has found an adversarial sequence of movement that causes the M model to never transition into a fireball generating state. This is a policy that looks great in the dream but fails completely in reality because the visit state that are outside the training distribution of M is a general ND problem with model-based RL. The solution the authors propose is to increase the temperatures tau of the M model during controller training. At tau equals to 0.1, the drain is almost deterministic. Monsters never shoot. The virtual score is over 2000, but the actual environment score collapsed to 193, barely above random. As we increase tau, the drain becomes harder and more predictable. At tau equals 1.15, the virtual score drops to around 900, but the actual environment scores peak at 1092, well above the required 750. The intuition is that a harder, noisier drain forces the controller to learn genuinely robust strategies rather than exploiting model imperfections. However, push tau too high, the drain becomes so chaotic, and the agent cannot learn anything useful either. So after training entirely inside the drain at tau equals 1.15, the controller is deployed to the real VizDoom environment for the first time. It achieves approximately 1,100 times step on average, far exceeding the 750 required to solve this task. The VAE is imperfect. It sometimes gets the number of monsters wrong, but an agent that has survived a noisy, uncertain nightmare generalizes robustly to the cleaner real environment. This is a compelling demonstration of the dream to reality transfer paradigm, and it foreshadows ideas that would later become important in simulation to real robotics research. The two experiments we saw use only a single iteration, train on random rollouts, then train the controller. For harder tasks, we need an iterative loop. Step 1, initialize everything randomly. Step 2, roll out in the real environment and collect data. Step 3, retrain M on all collected data and retrain C inside the updated drain. Step 4, repeat. The connection to neuroscience here is hippocampal replay replay. Which is the way the brain replaces recurring experiment during sleep to consolidate memories. So the authors suggest that like intrinsic motivation and curiosity rewards derived by flipping the sign of M's prediction laws can guide the agent to explore unfamiliar parts of the world to improve its model. It is important to acknowledge that the core ideas in this paper are not new. These diagrams are from Schmidhuber, 1990s paper, making the world differentiable. Left figure shows a controller with an internal RNN world models, and the right shows the same system in a feedback loop with an environment. The contribution of Ha and Schmidhuber 2018 is to take these foundational ideas from the earlier 1990s and demonstrate them at scale using modern deep learning components, convolutional VAEs, LSTM-based MDN-RNN, and GPU-accelerated training. The paper explicitly positioned itself as distillation and modernization of this earlier line of work. So the authors are very candid about several limitations. First, the VAE, the autoencoder, variational autoencoder is trained unsupervised, so it may encode irrelevant feature. In a Doom experiment, it reproduces decorative wall textures, but sometimes miss task-relevant road tiles in car racing. Training V jointly will reward prediction and could help, but then you lose the ability to reuse V for new tasks. Second, the LSTM has limitation. The limited capacity and suffers from catastrophic forgetting. It cannot store arbitrarily long histories. High capacity architecture like the transformers or models with external memory modules are natural future directions. Third, this approach is simulates the future step by step without any hierarchical abstraction or planning. The more general learning to think framework by Schmidhuber allows the controller to address subroutines of M for hierarchical reasoning, but that is left for the future work here. And to summarize, this paper proposed three-component agent architecture: V for spatial compression, M for temporal prediction with uncertainty, and C for minimal action selection. The key results are: first, full world models solves car racing V0 with a score of 906, the first reported solution. Second, an agent trained entirely inside a hallucinated VizDoom environment transfers successfully to the real game, scoring 1092, well above the 750 threshold. The temperature parameter tau is a practical tool for controlling the difficulty of the drain and preventing adversarial exploitation. An iterative training procedure extends the approach to more complex environments, and the underlying ideas connect deeply to both 1990s neural network research and modern neuroscience. And thank you for your attention. And if you have a question, please raise in the course forum. Thank you.